Most people, when they think about the end of the universe, picture something dramatic. A big crunch, everything collapsing back inward in a reversal of the Big Bang, matter compressed into a final singularity of infinite density and temperature. Or a big rip, dark energy tearing apart galaxies, then solar systems, then planets, then atoms, until space-time itself is shredded into disconnected fragments. Or a big freeze, stars burning out one by one, the universe cooling toward absolute zero, everything going dark and cold and still. These scenarios are frightening in the way that death is frightening. Final, irreversible, an ending. The universe runs down, exhausts itself, and stops. Whatever existed before is gone. The story ends. But what if the story does not end? What if the universe does not die? Not in the sense of reaching a final state from which nothing further can emerge. What if time continues? Not for billions or trillions of years, but forever. An eternity of time following the apparent end of everything, in which the laws of physics, still operating, still turning, produce events so rare and so bizarre and so fundamentally wrong feeling that they redefine what horror means in a cosmological context. This is not science fiction. The physics we are about to discuss is genuine, peer-reviewed, mathematically rigorous, and largely accepted as valid inference from well-established physical principles. What happens when quantum mechanics operates on an empty universe for long enough? What the laws of thermodynamics imply about events that are not merely improbable, but improbable to a degree that makes the word improbable meaningless. What it means for time to continue after meaning has stopped. What kinds of things the universe produces when it has been running long enough? Not just long enough to exhaust stars, but long enough to exhaust every physical process we can name, and then keep going, past the point where our language has useful words into timescales where the universe's own quantum nature turns against it and begins producing things that should not exist. The horrors of an eternal universe are not the horrors of destruction. They are the horrors of continuation, the horrors of a universe that keeps running after it should have stopped, that keeps producing events after it has run out of interesting things to produce, that eventually, given enough time, produces everything, including you, including this moment, again, not as a memory, as a fresh occurrence, spontaneous and causally unconnected to anything, in a universe that has forgotten everything that came before. The end of the universe is not the problem. The problem is what comes after the end. Let's go through it, in order, from the near future to the unimaginable far future, so that when we reach the horrors at the end, you understand exactly what the physics requires and why it requires it. Chapter 1: The timeline of everything. What the end actually looks like. Before we can talk about what comes after the end of the universe, we need to be precise about what the end means and when it arrives. Because the end of the universe is not a single event. It is a cascade of endings, each more total than the last, spread across timescales that dwarf each other by factors so large that every previous timescale becomes a rounding error. The physicist and cosmologist Fred Adams and his collaborator Greg Laughlin laid out this cascade in their 1999 book, The 5 Ages of the Universe. Building on their scientific papers that systematically worked through the long-term future of cosmological structure. Their framework divides cosmic time into 5 eras, each defined by the dominant physical process occurring during that era. The eras are defined on a logarithmic timescale. Time is measured as the power of 10 of the number of years since the Big Bang, so that the current age of the universe, 13.8 billion years, roughly 10 to the 10th power years, is at cosmological decade 10. We are currently in the stelliferous era, the era of stars. It began when the first stars ignited, roughly 100 to 200 million years after the Big Bang, and it will end when the last stars burn out. The stelliferous era is the era most people intuitively associate with the universe, the era of hydrogen being converted to heavier elements in stellar cores, of galaxies forming and evolving, of planetary systems accumulating, and, in at least one confirmed case, producing biology and civilization. The stelliferous era ends approximately 100 trillion years from now, 10 to the power of 14 years. At that point, all the hydrogen available for star formation will have been consumed or locked up in stellar remnants. The last stars to burn out will be the dimmest, smallest red dwarf stars, which burn their hydrogen so slowly that they will last far beyond any other type of star. The Sun has about 5 billion years remaining. The last red dwarfs will still be burning 1,000 times longer than that. But eventually, even the last red dwarf will exhaust its fuel, contract, and cool into a black dwarf, a cold, dark sphere of electron-degenerate matter that no longer produces any light or heat. The universe at 10 to the 14th power years is dark. Not dark like a cloudy night, dark like a universe in which every fire has been extinguished and no new fires can ignite. The skies of any surviving planet are black in every direction, lit only by the faint glow of cooling stellar remnants, and in the first few 100 trillion years, by the very faint light of the dimmest surviving red dwarfs. Then, as the last red dwarfs cool and dim, even this faint light disappears. The universe becomes a collection of cooling stellar remnants, black dwarfs, neutron stars, and black holes, moving silently through an expanding void. This is the degenerate era, roughly from 10 to the power of 15 to 10 to the power of 37 years. It is named for the fact that the dominant form of matter is degenerate matter, matter in which the quantum mechanical exclusion principle provides the primary pressure support against gravitational collapse, rather than the thermal pressure that supports normal matter and stars. Black dwarfs are degenerate. Neutron stars are degenerate. White dwarfs, which have not yet cooled to black dwarfs, are degenerate. The degenerate era is an era of slowly cooling remnants in an expanding, cooling, darkening universe. Within the degenerate era, several important processes occur. Gravitational interactions between objects and galaxies, the slow gravitational perturbations that objects exert on each other during their orbital motions, gradually cause some objects to be ejected from galaxies entirely, gaining energy from the gravitational interaction, and others to spiral inward toward the galactic center. Over timescales of roughly 10 to the power of 19 to 10 to the power of 20 years, most of the stellar remnants in a galaxy will either be ejected into intergalactic space or fall into the central black hole. The galaxy gradually dissolves, not violently, but through the slow gravitational evaporation of its constituents. The galaxy disperses into isolated stellar remnants, drifting through an expanding void, and the central supermassive black hole grows as it consumes the remaining infalling material. Also, Within the degenerate era, if the proton is unstable, which some extensions of the standard model of particle physics predict, protons will decay. The current experimental lower limit on the proton lifetime is approximately 10 to the power of 34 years, meaning the proton has not been observed to decay, and any decay must take at least this long. But some grand unified theories predict proton lifetimes in the range of 10 to the power of 36 years. If protons decay, black dwarfs and neutron stars slowly dissolve as their constituent protons decay into positrons and pions, which subsequently decay further. The energy from proton decay would heat these objects faintly, giving them a ghostly glow long after all other energy sources have been exhausted. If proton decay occurs, stellar remnants gradually evaporate over 10 to the power of 36 to 10 to the power of 40 years, leaving behind only a diffuse plasma of the decay products. Whether or not protons decay, the degenerate era ends and the black hole era begins as stellar remnants vanish and black holes become the dominant feature of the universe. This era runs from approximately 10 to the power of 40 to 10 to the power of 100 years. A span of time that dwarfs everything before it in the way that the universe's age dwarfs a single heartbeat. In the black hole era, the universe is populated almost entirely by black holes. The stellar mass black holes formed in supernovae. The supermassive black holes at galactic centers that have grown by accreting surrounding material over the preceding trillions of years. And the isolated black holes drifting in the expanding void. Everything else has either decayed, evaporated, or been accreted. The universe in the black hole era is nearly empty. Black holes are tiny compared to the distances between them, and the vast majority of the volume of the universe is featureless vacuum. But black holes are not permanent. Stephen Hawking showed in 1974 that black holes emit thermal radiation, Hawking radiation, from quantum mechanical effects at the event horizon. The temperature of this radiation is inversely proportional to the black hole's mass. A stellar mass black hole radiates at a temperature of tens of nanokelvin, far colder than the current cosmic microwave background, so negligible today that a stellar mass black hole is actually absorbing more CMB photons than it emits in Hawking radiation. But as the universe expands and cools, the CMB temperature drops, and eventually the Hawking temperature of the black holes exceeds the CMB temperature. At that point, black holes begin to lose mass through Hawking radiation faster than they gain it. The process accelerates as the black hole loses mass. Smaller black hole has a higher Hawking temperature, so it radiates more intensely, losing mass faster, raising its temperature further. The final moments of a black hole's evaporation are an explosive burst of radiation. For a stellar mass black hole, this complete evaporation takes approximately 10 to the power of 67 years. For a supermassive black hole of 1 billion solar masses, it takes approximately 10 to the power of 96 years. At approximately 10 to the power of 100 years, the number called a googol, which is where the technology company's name comes from, the last supermassive black holes have evaporated. Their final moments produce bursts of high-energy radiation that momentarily illuminate an otherwise dark universe, and then nothing. The black hole era ends. The universe contains nothing but the diffuse products of Hawking evaporation. extremely low-energy photons, and perhaps some neutrinos and gravitons, in a vast, cold, expanding space. This is the dark era, the final era, the apparent end. From here, the standard narrative of the universe's long-term fate concludes. The universe expands toward a state of maximum entropy, temperature asymptotically approaching absolute zero, energy density approaching nothing, no more events of any significance ever occurring. Heat death. The universe in this picture is dead in any meaningful sense by 10 to the power of 100 years. Nothing interesting can ever happen again. The story is over, except time continues. And that is where the horror starts. Chapter 2: What nothing actually means in quantum mechanics. The vacuum is not empty. To understand what happens after the apparent end of the universe, you need to understand something about the nature of nothing in quantum mechanics. Because in quantum mechanics, nothing is not nothing. The vacuum, the state of lowest possible energy, the state that the universe asymptotically approaches as all matter and energy disperses, is not an absence of activity. It is a seething, fluctuating, probabilistic medium in which events occur continuously, constrained only by the uncertainty principle and the conservation laws. This is not a metaphor. It is a precisely quantified physical reality with measurable consequences. The uncertainty principle, in one of its formulations, states that the product of the uncertainty in energy and the uncertainty in time for any quantum system cannot be less than a specific value, approximately h/4 pi, where h is Planck's constant. This means that for very short time intervals, the uncertainty in energy can be very large enough that the vacuum can borrow energy from nothing, use it to produce particle-antiparticle pairs, and then return the borrowed energy within the time allowed by the uncertainty principle. These are virtual particle-antiparticle pairs, not imaginary, not hypothetical, but measurable through the physical effects they produce. The Casimir effect, an attractive force between closely spaced metal plates in a vacuum caused by the difference in vacuum fluctuation modes between the plates and outside them, is a direct measurement of the reality of vacuum fluctuations. The Lamb shift, a small but precisely measured shift in the energy levels of hydrogen atoms, is caused by the interaction of the hydrogen atom's electron with virtual photons in the vacuum. These are real, measured, precision-tested effects of quantum vacuum fluctuations. The relevance of this to the long-term future of the universe is profound, even in a universe that has reached apparent heat death, with no matter, no radiation, no structure, just empty, expanding space. The vacuum is still there. The quantum fields that underlie all of reality are still there. They are fluctuating. They always fluctuate. They cannot stop fluctuating because stopping would require knowing both the field values and their rates of change simultaneously, which the uncertainty principle forbids. A vacuum that fluctuates is a vacuum that occasionally produces something, not a virtual particle pair that immediately annihilates. Those are the rapid fluctuations of the ordinary quantum vacuum. But given enough time, the fluctuations can occasionally produce configurations that persist, configurations that happen to have enough energy and enough structure to avoid immediate re-annihilation and instead develop into something more lasting. How much time is enough? That depends on what you want to produce. For small things, a single photon, a particle pair, the timescales are short. For larger things, a molecule, a rock, a planet, a star, the timescales are incomprehensibly longer. For the largest things, a galaxy, a structured universe, the timescales are so enormous that they cannot be expressed as numbers in any notation that fits in the observable universe. But in a universe of infinite or near infinite duration, even these timescales are finite fractions of the available time. This is the framework within which the horrors of the eternal universe operate. It is not a framework of destruction or collapse. It is a framework of probability and patience, of a universe that keeps running, keeps fluctuating, and given enough time, eventually produces everything that the laws of physics permit, including things that are deeply unsettling, including things that are familiar in deeply wrong ways, including you. And here is the crucial thing to hold on to as we proceed. The horror of the eternal universe is not the horror of something going wrong. It is the horror of things going exactly right, of physics working precisely as advertised, of the laws of quantum mechanics and thermodynamics, and gravity operating without exception for long enough that their implications become inescapable. The horrors of an eternal universe are not glitches. They are features. They are what you get when correct physics runs for infinite time. The discomfort they produce is not evidence against the physics. It is evidence of how strange the correct physics actually is. Chapter 3: Boltzmann Brains, the most disturbing prediction in all of physics. In the late 19th and early 20th century, the Austrian physicist Ludwig Boltzmann was wrestling with a paradox in thermodynamics. The second law of thermodynamics states that entropy, the measure of disorder in a system, always increases in a closed system. The universe started in a very low entropy state. The Big Bang, highly ordered, extremely low entropy, and has been increasing in entropy ever since. This gives time its arrow, the reason the past is different from the future, the reason eggs break but don't unbreak, the reason heat flows from hot to cold and not the reverse. But here was Boltzmann's problem. If the universe is eternal, which many 19th century physicists assumed, and entropy can only increase, eventually the universe reaches maximum entropy, thermal equilibrium, and stays there. But in an eternal universe, there is always some probability, no matter how small, of a spontaneous fluctuation downward in entropy, a temporary, spontaneous decrease in disorder caused by the random thermal motion of molecules conspiring, for a moment, to produce a more ordered configuration. In a finite time, this is so unlikely as to be irrelevant. But in an infinite time, it is guaranteed to happen. Eventually, in an eternal universe, the random thermal fluctuations will conspire to produce something ordered. What is the simplest possible ordered object that could spontaneously nucleate from a high-entropy thermal bath or a fluctuating quantum vacuum? The philosopher's answer would be the smallest possible thing that counts as an observer, the smallest thing capable of having experiences and perceiving a world. Because we know observers exist, we are one, and we need to explain why. And in an eternal universe, the most probable explanation for the existence of an observer is not the extremely unlikely process that produced you, billions of years of stellar evolution, planetary formation, biological evolution, and the entire history of human civilization, but rather the far less unlikely process of a spontaneous quantum fluctuation that produces directly the minimum viable observer. This minimum viable observer, spontaneously nucleated from the quantum vacuum, complete with false memories of a past that never happened, perceiving a world that may not be real, existing for the brief moment before the fluctuation reverses and it dissolves back into the vacuum, is called a Boltzmann brain. The name is somewhat whimsical, but the concept is deadly serious. A Boltzmann brain is a self-aware observer that forms through a random quantum or thermal fluctuation rather than through any physical process of evolution or development. It has all the characteristics of a conscious entity: experiences, apparent memories, a sense of self, the perception of a surrounding world, but its surrounding world is not real. It is simply the set of false memories and false perceptions that happened to be included in the fluctuation that produced it. The Boltzmann brain exists for a moment, perhaps microseconds, perhaps less, before the fluctuation responsible for it reverses and it ceases to exist. During that moment, it experiences something. It may, if sufficiently complex, wonder where it came from. It may perceive itself as sitting at a desk, or walking through a city, or watching a video about the universe. All of these perceptions are false. There is no desk, no city, no universe of the kind it perceives. There is only the fluctuation and the brief consciousness it contains. Why is this relevant to the far future of the universe? Because in a universe that continues for long enough, the rate at which Boltzmann brains spontaneously nucleate from the vacuum eventually exceeds the rate at which genuine observers are produced by ordinary physics. In the stelliferous era, the era of stars and planets and biology, genuine observers like us are produced by physical processes at a rate vastly exceeding the nucleation rate of Boltzmann brains. Boltzmann brains do nucleate, but they are overwhelmingly outnumbered by genuine observers. We have overwhelming statistical reason to believe we are genuine observers rather than Boltzmann brains. But wait long enough, into the dark era, past the death of the last black hole, into the age of the quantum vacuum alone, and the genuine observer production rate drops to zero, while the Boltzmann brain nucleation rate, though extraordinarily slow, is not zero. Given enough time, the vacuum produces more Boltzmann brains than the entire stelliferous era produced genuine observers. In fact, given infinite time, the vacuum produces infinitely many Boltzmann brains, and each one of them, in its brief moment of existence, is an observer. This creates one of the most disturbing problems in cosmology, the Boltzmann brain problem. If the universe is eternal or effectively eternal, and if Boltzmann brains nucleate at any finite rate, then the overwhelming majority of observers in the universe are Boltzmann brains, which means that any given observer, any self-aware entity capable of asking, "What am I?" is overwhelmingly more likely to be a Boltzmann brain than a genuine observer produced by normal physical processes, including you. The uncomfortable implication is this: if you are reading or watching this, the prior probability that you are a Boltzmann brain with false memories of having watched this, rather than a genuine person who actually watched it, is not zero. In an eternal universe, it is actually much higher than the probability that you are genuine, because Boltzmann brains vastly outnumber genuine observers. The fact that your experience seems coherent and consistent, that you seem to have continuous memories, that the world around you seems to follow consistent physical laws. None of this is evidence against being a Boltzmann brain, because a Boltzmann brain's false memories include all of these things. A Boltzmann brain that believes it is a genuine observer, sitting in a consistent world, watching a late science video, is indistinguishable from you, from the inside. Most physicists do not seriously believe they are Boltzmann brains, but the fact that a physically plausible cosmological model, an eternal universe with a non-zero Boltzmann brain nucleation rate, predicts that the vast majority of observers are Boltzmann brains is taken very seriously as a constraint on cosmological models. Specifically, any cosmological model that predicts an eternal universe with a non-zero vacuum energy is in trouble, because it predicts a Boltzmann brain domination that makes it essentially impossible for any observer to conclude they are genuine rather than a fluctuation. This is called the Boltzmann brain problem, and it is an active area of research in theoretical cosmology. Multiple proposed solutions exist, all of them requiring specific constraints on the cosmological model. But the problem itself is real. The physics behind it is real. And the implication that in an eternal universe, most observers are not what they think they are, is one of the most genuinely unsettling things that careful physics has produced. There is a further layer to the Boltzmann brain problem that makes it even more uncomfortable. Most people, when first encountering the concept, feel a reflexive confidence. Of course I am not a Boltzmann brain. I have continuous memories. My experience is coherent. The world around me follows consistent physical laws. I have relationships and history, and a body that works in predictable ways. All of these feel like evidence of being genuine rather than a spontaneous fluctuation. But consider, these are exactly the things a Boltzmann brain would also have. A Boltzmann brain is not a confused or incoherent observer. It is a self-consistent observer whose false memories are internally consistent, whose apparent perceptions follow apparent physical laws, whose apparent history includes continuous experience. The Boltzmann brain's internal experience is indistinguishable from a genuine observer's internal experience by construction. Because the Boltzmann brain is defined as a fluctuation that produces the complete subjective state of an observer, including all the coherence and consistency and apparent history that the genuine observer has. The coherence of your experience is not evidence against being a Boltzmann brain. It is the very thing the Boltzmann brain was constructed to replicate. Every argument you make from the inside for your own genuineness is an argument that a Boltzmann brain would make equally, and the Boltzmann brain would be wrong. The question of whether you specifically are wrong is not answerable from the inside, which is precisely what makes it so deeply unsettling. Chapter 4, Poincaré Recurrence, the Universe Returns. In 1890, the French mathematician Henri Poincaré proved a theorem that, when applied to the universe, produces one of the most mind-bending results in all of physics. The Poincaré recurrence theorem states that any finite, bounded physical system in which energy is conserved will, given sufficient time, return to a state arbitrarily close to its initial state. It will recur, not just once, infinitely many times, in a sequence of recurrences that continue without end. The proof is elegant and purely mathematical. Consider a system with a finite number of possible states, or more precisely, a system with a finite phase space, the mathematical space of all possible configurations of the system. If the system's dynamics are measure-preserving, meaning the volume of any region of phase space is preserved under the system's time evolution, then the system cannot escape to some distant region of phase space and stay there. It must eventually return to near its starting point. The theorem is a consequence of the pigeonhole principle scaled up to infinite time. In a finite space, if you keep moving, you must eventually revisit somewhere near where you have been. The theorem applies, in principle, to the universe if the universe is finite in volume and its dynamics are described by Hamiltonian mechanics, which conserves phase space volume. Whether the actual universe satisfies these conditions is debated. The universe may be infinite in volume, or its dynamics at the quantum level may not be precisely Hamiltonian, but the theorem applies to any sufficiently large but finite region of the universe, and the implications are extraordinary. Applied to the current state of the observable universe, the Poincaré recurrence theorem implies that the universe will, given sufficient time, return to a state virtually identical to its present state. Not a state similar to the present in broad strokes, but a state in which every particle, every photon, every quantum field is configured in a way that is indistinguishable to any physical measurement from the present configuration of the universe. The stars will be back in their current positions. The planets will be in their current orbits. The Earth will exist in its current state. Every person alive today will have an exact physical counterpart in the recurred universe. How long does this take? The Poincaré recurrence time for the observable universe is not a number that can be written meaningfully in decimal notation. It is often expressed as 10 to the power of 10 to the power of 10 to the power of in a tower of exponents that itself cannot be written in any notation that fits within the observable universe. The recurrence time is so incomprehensibly larger than any timescale we have discussed. Larger than 10 to the power of 100. Larger than 10 to the power of 10 to the power of 100. Larger than anything with a name, that it is essentially meaningless as a number in any practical sense. But in an eternal universe, time is available without limit. The recurrence time, however large, is a finite duration in an infinite timeline. The universe will recur, and then it will recur again and again, infinitely many times. Every moment that has ever existed will exist again in exact physical detail infinitely many times. Every moment of joy, every moment of suffering, every moment of significance and insignificance in the history of everything, repeated exactly, endlessly, forever. There is a deeply disturbing logical structure to this. In a Poincaré recurrence of the current universe, every person alive today has an exact physical copy. That copy has all the memories of the original. It experiences everything the original experienced. From the inside, the copy is indistinguishable from the original. The copy does not know it is a copy, has no memory of the unimaginable eons that have passed since the original existed, and experiences itself as the seamless continuation of a life that actually ceased an incomprehensible time ago. The copy is not the original, but the copy cannot know this. Now multiply this by infinitely many recurrences, each separated by the same incomprehensible intervals, and consider what this means for identity and continuity. In what sense does you refer to a specific individual? If every physical state you have ever occupied will be recreated exactly, infinitely many times. In what sense does the history between recurrences matter if there is no continuous thread of experience connecting the original to the copy? The Poincaré recurrence theorem, applied to an eternal universe, produces a kind of cosmic eternal return that strips identity of any stable meaning, not by destroying individuals, but by recreating them endlessly with no connection to the original except physical identity of state. Nietzsche proposed the eternal return as a philosophical thought experiment. Imagine that your life repeats infinitely, exactly as it is, with no variation, no escape. How would you live knowing this? He intended it as a test of affirmation. Can you affirm your life so completely that you would choose to live it again, forever? But the Poincaré recurrence is not a philosophical thought experiment. It is a mathematical theorem. The eternal return is not a challenge to your values. It is a feature of the physics of an eternal universe. There is something additionally disturbing about the structure of Poincaré recurrence that often goes unstated. The recurrences are not continuous. They do not occur in smooth succession with some thread of experience connecting them. Between two recurrences of the current state of the universe lies an interval of time more vast than the entire span between the Big Bang and the recurrence. An interval populated by nothing recognizable, nothing structured, nothing that resembles the universe as it is now. The recurrence arrives not as a continuation of experience, but as a fresh instantiation of the same physical state in a context utterly alien to it. The copy of you in a Poincaré recurrence is not you having lived through the interval since the first occurrence. It is you with no knowledge of the interval, with all the memories of the original you, in a universe that has returned to the same physical configuration after an inconceivable journey through different configurations. The recurrence is not continuation. It is repetition without connection. The distinction matters because it strips the recurrence of any consolatory character, any sense in which the eternal return of your life is also the continuation of your experience. Your experience does not continue. The physical configuration that contains your experience repeats. These are not the same thing, and the gap between them is the gap between living and being copied. Chapter 5. False Vacuum Decay. The Universe's Self-Destruct Button. So far, we have been discussing what happens if the universe continues as it is, if the laws of physics remain constant, and the vacuum remains stable. But there is another possibility, one that physicists consider entirely plausible, and that several current cosmological observations are consistent with. The vacuum of our universe may not be in its lowest possible energy state. The vacuum of quantum field theory is not simply nothing. It is the ground state of the quantum fields that pervade all of space, the lowest energy configuration of those fields. But lowest energy is a relative concept. A physical system can be in a local minimum of its energy landscape, a state that requires some perturbation to escape from, rather than a global minimum, the absolute lowest possible energy state. A ball sitting in a valley on a hillside is at a local minimum of gravitational potential energy. It is lower than its surroundings, but it is not at the absolute lowest point, sea level or the bottom of the hill. It is, in technical language, a metastable state. The current vacuum of our universe, the specific values of all quantum fields throughout all of space, may be in exactly this situation. It may be a false vacuum, a metastable state that is lower in energy than the surrounding configurations, but not at the absolute minimum. If this is the case, then quantum tunneling, the quantum mechanical process by which systems can transition from one state to another, even without the energy to classically surmount the barrier between them, can, with some tiny probability, trigger a transition from the false vacuum to the true vacuum. This is false vacuum decay. What happens if false vacuum decay occurs? The true vacuum, by definition, has lower energy than the false vacuum. The transition from false to true vacuum releases this energy difference. It is energetically favorable. A bubble of true vacuum nucleates at some point in space and immediately expands outward at the speed of light. Inside the bubble, the quantum fields have settled into their true minimum configuration, which means the constants of physics, the masses of particles, the strengths of forces, everything that we describe as the laws of nature, are different. The laws of physics as we know them exist only in the false vacuum. Inside the expanding bubble of true vacuum, the laws are different and almost certainly incompatible with the existence of any structure, any matter, any physics that resembles what we experience. The bubble wall expands at the speed of light. You cannot see it coming. You cannot detect it in advance, because the only signal of its approach would be light or particles traveling it, or below the speed of light, from the bubble wall's previous position. And the bubble wall is traveling at the speed of light, so any signal it might emit arrives simultaneously with the wall itself. You would receive no warning. The bubble would arrive, and in an interval shorter than the time it takes a neuron to fire, the false vacuum of our universe would be converted to the true vacuum throughout the space occupied by your body, every atom of which would be instantaneously restructured or destroyed by the change in the laws of physics. This is not a slow, progressive destruction. It is not like being hit by radiation or a shock wave. It is the cessation of the specific set of physical laws that allows you to exist as a physical system. The moment the bubble wall passes through your location, the false vacuum that has been sustaining your atoms, and the atoms themselves, and every interaction between them, ceases. Whatever the true vacuum is, it is not the environment that produced or supports you. The transition is instantaneous and total. The most disturbing aspect of false vacuum decay, beyond the obvious destruction it implies, is its randomness. The nucleation of a false vacuum decay bubble is a quantum tunneling event. It can occur anywhere in space at any time. There is no mechanism that warns of its approach, no physical sign that it is imminent, no accumulation of stress or strain in the vacuum that precedes it. The decay probability per unit volume per unit time is determined by the specific quantum field theory of the vacuum, and we do not know its value. We do not know if our vacuum is false. We do not know how close to a true vacuum it is. We do not know whether we are in a metastable state or a genuinely stable one. The Higgs field, which gives mass to elementary particles and whose value defines key features of the laws of physics, is a specific candidate for the false vacuum instability. Calculations based on the measured mass of the Higgs boson, discovered at CERN in 2012, and the measured mass of the top quark suggest that the current configuration of the Higgs field is near the boundary between stability and metastability, what physicists call the edge of stability. Some calculations suggest the universe is in a metastable Higgs vacuum that could tunnel to a lower energy state. The lifetime of this metastable state is estimated to be extremely long, far longer than the current age of the universe, perhaps longer than 10 to the 100th power years, but not infinite. This is worth sitting with. The measurement of two numbers, the Higgs mass at 125.25 gigaelectronvolts and the top quark mass at approximately 173 gigaelectronvolts, places our universe in a region of parameter space where the long-term stability of the vacuum is uncertain. The uncertainty is not large in the sense of being equally likely stable or unstable. Most calculations suggest our vacuum is stable or at least very long-lived. But the fact that the universe's vacuum stability is a quantitative question with a non-obvious answer derived from particle physics measurements made at the Large Hadron Collider is extraordinary. We are measuring the vacuum stability of the universe with a machine buried under the Franco-Swiss border, and the answer is probably fine, but not certainly fine. This is not a comfortable answer for anyone who has thought carefully about what false vacuum decay implies. There is one saving grace from a human perspective, if saving grace is the right phrase for something this large. If our universe is in a metastable false vacuum, and if a true vacuum bubble has already nucleated somewhere in the universe's past, then the bubble is currently expanding outward at the speed of light and will eventually reach us. But we will have no warning, and if it has not yet nucleated, the nucleation is random, unpredictable, and could happen at any point in space, including in our immediate vicinity, at any moment. The probability per unit time per unit volume is thought to be extremely small, but it is not zero, and there is no physical mechanism that prevents it from happening right now. The only comfort is that by the time you read or hear the word now, the moment has already passed, and you are still here. If false vacuum decay occurs, it doesn't just end the universe in the region it reaches. It ends the specific physical laws that define our universe throughout the volume swept by the expanding bubble, and the bubble expands forever at the speed of light, converting everything it touches. It is not merely the death of stars and planets and life. It is the erasure of the framework within which stars and planets and life were possible. A universe that experiences false vacuum decay does not merely die, it is replaced by something with entirely different physics, within which none of the structures of our universe can exist and from which none of the information of our universe can be recovered. Chapter 6: The End of Black Holes. Hawking radiation and the final evaporation. Let us return to the timeline. We are at approximately 10 to the power of 100 years, a Google years from now, and the last black holes are evaporating. This process deserves more attention than it usually receives, because the final moments of a black hole's evaporation are one of the strangest and most consequential events in the universe's history. Hawking radiation arises from quantum effects near the event horizon of a black hole. In simple terms, near the event horizon, quantum vacuum fluctuations produce virtual particle-antiparticle pairs. Normally, these pairs annihilate almost immediately. But at the event horizon, it occasionally happens that one particle of the pair falls inside the horizon while the other escapes. The infalling particle has negative energy from the perspective of observers outside the black hole. It effectively removes energy from the black hole, reducing its mass. The escaping particle has positive energy and appears to an outside observer as radiation emitted by the black hole. The black hole slowly loses mass through this process, radiating with a thermal spectrum at the Hawking temperature, which is inversely proportional to the mass. As mass decreases, temperature increases. As temperature increases, the rate of energy loss increases. The process accelerates. The final moments of a black hole's evaporation, when its remaining mass has dropped to the Planck mass, approximately 2.2 times 10 to the power of -8 kilograms, the mass scale at which quantum gravity effects become significant, are unknown in detail because they require a quantum theory of gravity that we do not have. The current expectation is that the final evaporation produces a burst of high-energy radiation, an explosion in effect, as the remaining mass is converted to radiation essentially instantaneously. For a stellar mass black hole, this final burst releases energy equivalent to millions of nuclear weapons. For a supermassive black hole of 1 billion solar masses, the final burst is proportionally more energetic. These final explosions are among the last energetic events in the universe, brief flashes of gamma radiation and particle emission in an otherwise dark and quiet cosmos. After the final black hole has evaporated, the universe contains essentially nothing material. The energy of the Hawking radiation has dispersed into the expanding universe, red-shifting to lower and lower energies as the universe continues to expand. The temperature of the universe approaches, but never quite reaches absolute zero. The photons and other particles from Hawking evaporation grow increasingly sparse and low energy, spread through an increasingly vast volume of space. This is the apparent end, but the quantum vacuum persists. The uncertainty principle persists. The laws of physics persist. And with them, the possibility of quantum fluctuations producing things that, in any finite time, would be negligibly rare, but in an infinite time, inevitable. Chapter 7. Quantum tunneling at the largest scales. When the impossible becomes inevitable. Quantum tunneling is one of the most counterintuitive features of quantum mechanics. It allows physical systems to transition between states that are classically forbidden, states that would require the system to pass through an energy barrier that it does not have enough energy to surmount. Tunneling occurs because in quantum mechanics, particles and systems do not have precise positions and energies. They are described by probability waves, and those waves extend into classically forbidden regions. There is always some probability, however small, of finding the system on the other side of the barrier. Tunneling is not exotic or speculative. It is the mechanism by which nuclear fusion occurs in the Sun at temperatures lower than classical physics would require. It is the mechanism by which radioactive decay occurs. The alpha particles in radioactive nuclei tunnel through the nuclear potential barrier. It is the mechanism used in tunnel diodes and scanning tunneling microscopes. It is a routine, well understood, experimentally verified feature of quantum mechanics. Applied to large systems, systems that are complex and massive, The probability of tunneling decreases dramatically with the complexity of the system. The probability of tunneling is proportional to e to the power of minus s, where s is the action associated with the tunneling path, which increases with the mass and complexity of the system. For everyday objects, the tunneling probability is so small as to be completely negligible on any timescale, less than the current age of the universe raised to astronomical powers. A rock does not spontaneously tunnel through a wall in any practically meaningful sense. But in an infinite time, even these astronomical odds are beaten. What can quantum tunneling produce given infinite time? In principle, anything that the laws of physics permit. A single photon can tunnel across the universe. A single atom can quantum mechanically tunnel from one location to another. A molecule can tunnel into a specific arrangement. Given enough time, a region of vacuum can quantum mechanically fluctuate into a configuration that contains a rock, or a planet, or a star, or an entire galaxy. The timescales for these events are incomprehensibly vast. The tunneling time for a macroscopic object, even a small one, to spontaneously appear through quantum fluctuation is not 10 to the power of 100 years. It is not 10 to the power of 10 to the power of 100 years. It is a number expressed as a tower of exponentials so tall that it cannot be written in any notation that fits within the observable universe. But in an eternal universe, these timescales are merely long waits. The universe has infinite time to wait. What emerges from quantum fluctuations is not constrained to be simple. Given enough time, the vacuum will produce a fluctuation containing every configuration of matter that is consistent with the laws of physics. This means, eventually, a fluctuation containing a complete, self-consistent macroscopic structure, a complete planet, or to a complete star system, a complete galaxy, a complete observable universe exactly mimicking the one we inhabit, but without any causal connection to the history that produced our observable universe. A spontaneous universe, nucleated from the quantum vacuum, containing within it every galaxy and star and planet and life form that our universe contains, including every human being who has ever lived. Including you. Including this exact moment. Including the specific configuration of your brain as you process this information. This is the Boltzmann Brain problem extended to its most extreme conclusion. Not just individual brains, entire Boltzmann universes, complete with their own apparent history and physical laws and contents, arising spontaneously from quantum fluctuations and lasting for some period before dissolving back into the vacuum. In an eternal universe, they arise infinitely often, and the overwhelming majority of observers, including every observer in a Boltzmann universe who believes themselves to be in a genuine, causally connected universe, are wrong about the nature of the reality they inhabit. Chapter 8: The Dark Era. What infinity actually feels like. We have established the timeline. By 10 to the power of 100 years, the last black holes have evaporated. The universe contains nothing but the cold, dispersed remnants of Hawking radiation, extraordinarily low-energy photons and other particles spread across an expanding void of effectively infinite extent. No stars, no planets, no structures of any kind, no chemistry, no biology, no information processing of any recognizable form. Just the quantum vacuum, expanding, cooling, fluctuating at the microscopic scale in ways invisible to any macroscopic observation. This is the Dark Era. It begins at approximately 10 to the power of 100 years, and it does not end. It is the permanent state of the universe, from which the only departure is through the quantum fluctuation events we discussed in the previous chapter. Boltzmann Brains, Poincaré recurrences, spontaneously nucleated structures of arbitrary complexity. These events occur, but they are separated by timescales so enormous that even the 10 to the 100-year lifespan of the universe so far is negligible in comparison. What the Dark Era actually feels like, to the extent that any subjective framing is appropriate for a state that contains no subjects, is something worth dwelling on, because it forces a confrontation with what infinity actually means as a physical reality rather than an abstract concept. Consider the first Poincaré recurrence of the observable universe. The time for this event, the time for the universe to spontaneously return to a state indistinguishable from its present configuration, is approximately 10 to the power of 10 to the power of 10 to the power of 56 years. Let us try to comprehend this number, knowing in advance that we cannot. The current age of the universe is 10 to the power of 10 years. The end of the stelliferous era is 10 to the power of 14 years. The end of the degenerate era is 10 to the power of 40 years. The end of the black hole era is 10 to the power of 100 years. Each of these numbers is enormously larger than the last. Now consider 10 to the power of 10 to the power of 10 to the power of 56. The exponent in this number is 10 to the power of 10 to the power of 56. The exponent of that exponent is 10 to the power of 56, which is itself 100 septendecillion, a number already beyond all reasonable intuition. And 10 to the power of 10 to the power of 56 is 10 raised to the power of 100 septendecillion. And 10 to the power of 10 to the power of 56 is 10 raised to the power of that. And the Poincaré recurrence time is 10 raised to the power of that final tower. At some point, the numbers stop being numbers in any practical sense and become notations for pure incomprehensibility. This is what infinity feels like from the inside of a physical description of the universe. Not an abstract limit approached from below, but a concrete duration that the universe occupies, during which the timescales involved become so large that they cannot be processed by any finite physical system. The Poincaré recurrence time is finite. It will be reached, but it is so many orders of magnitude beyond the death of the last black hole that the death of the last black hole, which we treated as the end of the universe, is not even a beginning. It is not a first moment. It is not even a detectable fraction of the full duration of the Dark Era before the first recurrence. And after the first recurrence, the universe returns to something like its present state, exists in that state for another 13.8 billion years or so, ages and cools again through all the same eras, reaches another dark era, fluctuates for another incomprehensible span, and eventually has its second Poincaré recurrence, and then its third, and its fourth. Infinitely many times, without end, each recurrence separated from the last by an interval that makes the interval before the first recurrence look short. There is a specific thought experiment that makes the incomprehensibility of the Dark Era's timescales more visceral, even if it cannot make them comprehensible in any meaningful sense. Imagine a being, a hypothetical immortal observer, who exists in the dark era with full awareness of the passage of time. They have been alive since the end of the black hole era and will remain alive forever. They have watched every Boltzmann brain fluctuation arise and dissolve. They have watched every spontaneous nucleation of structure, the occasional appearance of a molecule, a rock, a small star, a short-lived galaxy, each separated from the last by intervals beyond measure. By the time of the first Poincaré recurrence, how long has this observer been waiting? The number defies any answer that communicates experience. They have been waiting for 10 to the power of 10 to the power of 10 to the power of 56 years. This is not a long wait in the way that a century is a long wait, or a millennium is a long wait, or the age of the universe is a long wait. It is long in a category beyond all of these, a duration that exceeds any referent by factors that themselves exceed any referent. If the observer tried to count the seconds of their waiting, 1, 2, 3, they would count beyond 10 to the power of 10, to the power of 10, to the power of 56, times 3 times 10, to the power of 7 seconds, since there are roughly 3 times 10 to the 7th power seconds in a year. The counting would never complete. The observer would spend more time counting than the entire age of the universe as it currently stands, in every second of their counting, and still be nowhere near finished. This hypothetical immortal observer has no meaningful way to experience the passage of this time, because the experience of duration requires reference points, events to mark the passage, differences between moments to make some moments distinct from others. In the dark era, events are so rare that the intervals between them exceed the span of any experience. The observer's subjective duration between events is not a feeling of boredom or waiting. It is a void of experience so complete that the very concept of passing time ceases to apply in any experiential sense. The dark era is not experienced as long. It is not experienced at all by any observer who requires events to mark the passage of moments. It simply is, in all its incomprehensible extent, whether anyone is there to experience it or not. The horror of the dark era is not that it is dark. It is that it is long, longer than long, longer than any modifier of long that the English language contains. And throughout this incomprehensible duration, the universe is not nothing. It is the quantum vacuum, fluctuating, producing its occasional structures, and observers and recurrences, each one disconnected from the last by an interval that contains nothing of recognizable significance. The dark era is not peaceful emptiness. It is endless repetition without memory, production without purpose, observers without context, arising and dissolving in a void that has forgotten everything that preceded them and will forget them too before the next fluctuation produces another transient observer who also has no idea where they came from or what the vast darkness around them means. Chapter 9: The last information, the death of memory itself. Before we go further into the horrors of the eternal universe, there is a specific event that deserves its own chapter. The moment when the last coherent piece of information in the universe is destroyed. Not the end of energy, not the end of matter, but the end of order. The moment when the last structure capable of encoding any information dissolves, and the universe's history becomes, in a precise information theoretic sense, unretrievable. Information in physics is not the same as the colloquial meaning of the word. Physical information is a precise concept. It refers to the specific configuration of a physical system, the arrangement of its constituent parts in a specific state that distinguishes it from other possible states. A book contains information not because it has meaning, but because the arrangement of ink on its pages is specific, distinguishable from the vast number of alternative arrangements the same ink and paper could take. A brain contains information because the specific pattern of its neural connections and electrochemical states distinguishes it from all other possible configurations of the same matter. The laws of quantum mechanics, specifically the principle of unitarity, require that information is conserved. In an isolated quantum system, the total amount of information is preserved. Physical processes can scramble or redistribute information, but cannot destroy it. This is a deep principle of quantum mechanics that has been confirmed in every experimental test and that underlies the black hole information paradox. The question of what happens to the information about the matter that falls into a black hole, which Hawking originally argued was destroyed, but which most physicists now believe is preserved in some form, possibly encoded in the subtle correlations of the Hawking radiation. But information conservation does not mean information remains accessible or useful. As entropy increases, information becomes increasingly scrambled, spread through the correlations between particles in ways that require ever more resources to extract. By the end of the Stelliferous era, the information about the specific history of a star, the details of its formation, its composition, the lives it supported, is not destroyed, but it is encoded in the correlations of billions of dispersed atoms and photons, irretrievably scrambled for any practical purpose. The information exists but is inaccessible. As the black hole era ends and the last Hawking radiation disperses, the last coherent encoding of historical information, whatever information was preserved through the black hole evaporation process, dissolves into the thermal radiation of the expanding universe. The photons from this radiation continue to exist. The correlations between them, which carry the scrambled information, continue to exist in principle. But the universe expands, and as it expands, the wavelengths of these photons stretch. They become lower and lower in frequency, lower and lower in energy. Their ability to interact with anything, to be detected, to carry a signal, to participate in any process that could be called information transfer, decreases as their energy decreases. Eventually, the photons have wavelengths comparable to the size of the observable universe. At this point, they are not meaningfully photons in any operational sense. They are quantum fluctuations of the electromagnetic field at the scale of the horizon. They carry correlations, but those correlations cannot be measured by any physical system small enough to fit within the accessible region of the universe, because any such measurement system would have less information processing capacity than the number of bits required to specify the correlations. What this means, in practical terms, is that the universe's history becomes completely inaccessible at some point during the dark era. Not destroyed, the correlations are there, in principle, somewhere in the quantum state of the universe, but as inaccessible as if they had been destroyed, because no physical system that could ever exist within the causally accessible universe could perform the measurements needed to extract them. The past becomes not just forgotten, but unrecoverable, not by any observer that the laws of physics permit to exist. It is worth tracing the process of information loss in more detail, because the specific sequence of events illuminates what is lost and when. In the stelliferous era, information is being produced continuously. Stars encode the history of the nebulae from which they formed in their elemental compositions. Planets encode the history of their formation in their geological records. Biospheres encode the history of their evolution in the genomes of their organisms. This information is constantly being partially scrambled. Stars explode and disperse their information into the interstellar medium. Geological records are overwritten by volcanic activity and erosion. Species go extinct and their genomic information is lost. But the rate of information production exceeds the rate of information loss during the stelliferous era. The universe's total information content, in the sense of the complexity of its structures, grows throughout the era of stars. As the stelliferous era ends and the degenerate era begins, the rate of information production declines, and the rate of information scrambling begins to dominate. The information encoded in living systems, the most complex information structures in the known universe, dissolves as biospheres collapse and the planets that hosted them cool. The information encoded in civilizations, language, art, science, history, dissolves as the civilizations cease and their physical records disperse. This information is not destroyed in the quantum mechanical sense, but it is scrambled into the thermal radiation and dispersed matter of the cooling universe in ways that are for any practical observer irrecoverable. By the time the black hole era ends, the only remaining coherent information structures are the black holes themselves, or more precisely, the subtle correlations in the Hawking radiation they have emitted. If Hawking radiation preserves information, as most physicists now believe, following the black hole, information paradox resolution proposed by Juan Maldacena and others through the ADS/CFT correspondence, then the information about everything that fell into each black hole during its lifetime is encoded in the complex quantum correlations of the radiation the black hole has emitted. This information is real, quantum mechanically, but it is spread across the entire expanse of the expanding universe, in correlations between individual photons separated by cosmological distances. No physical system of any kind, no computer, no civilization, no observer, could ever gather enough of these photons and perform enough measurements to recover the encoded information. The information exists, but is functionally identical to being gone. This is the death of memory at the cosmic scale. Not merely the death of specific memories, the memories of civilizations and individuals and experiences that are lost with the deaths of the minds that held them, but the death of the cosmic record itself, the physical imprint of history in the configuration of matter and energy, becoming so scrambled, so diluted, so stretched by expansion that no physical system within the universe can ever access it. The universe in the dark era has not merely forgotten its history, it has become physically incapable of remembering it. It is a universe without a past in any operationally meaningful sense, a universe of perpetual present, fluctuating forward without reference to anything that came before. This is, I would argue, the most structurally complete horror in the list. Not the Boltzmann Brains, which are disturbing because of what they imply about individual identity. Not the Poincaré recurrence, which is disturbing because of what it implies about continuity and meaning. But the death of memory itself, the progressive erasure of the universe's capacity to know what it has been. Because it means that even the horrors we have been describing, even the Boltzmann brains, and the recurrences and the false vacuum decays, occur in a context where the universe has lost the ability to connect any event to any other event through a record. Each event in the dark era occurs in a void, not just of matter, but of context. The universe is not building toward anything. It is not coming from anything it can remember. It is simply the fluctuating quantum vacuum, producing events that are connected to nothing and will be remembered by nothing in a duration that has no reference to the history that preceded it. Chapter 10. De Sitter Space and the Cosmological Horizon, the prison that never opens. In an accelerating universe, which ours appears to be, driven by dark energy that is causing the expansion to speed up rather than slow down. The long-term geometry of space-time is called de Sitter space, named for the Dutch mathematician and physicist Willem de Sitter, who found this solution to Einstein's field equations in 1917. De Sitter space describes a universe with a positive cosmological constant, dark energy, expanding exponentially. In de Sitter space, every observer is surrounded by a cosmological event horizon, a boundary beyond which the expansion of space carries things away, faster than light can travel. Nothing beyond the event horizon can ever communicate with or affect the observer. The event horizon is not a physical wall. You could cross it without noticing anything special at the moment of crossing. But it is a causal boundary. Once beyond it, you are permanently beyond the observer's causal reach. For our universe, the cosmological event horizon currently sits at approximately 16 billion light-years from Earth. Galaxies beyond this distance are already causally severed from us, in the sense that any signal we send today will never reach them, because the expanding space between us and them is growing faster than light can cross. Galaxies are currently being carried beyond our event horizon all the time. Each galaxy that passes beyond the horizon is lost permanently, its light red-shifting toward infinite wavelength as the galaxy recedes. Eventually, only the galaxies of the local group remain within our causal reach. The rest of the observable universe has been permanently severed, carried beyond the horizon by the accelerating expansion, their light arriving ever more faintly until it finally stops arriving at all. This is happening right now, on cosmological timescales. The universe we can see is not the universe that will be accessible to our distant descendants. With each passing billion years, more and more of the universe moves permanently beyond our reach. The observable universe is shrinking, not in the sense that galaxies within it are moving closer together, but in the sense that the set of galaxies we can ever affect or receive information from is contracting as dark energy carries more of them beyond the event horizon. We are becoming, progressively, more isolated. The universe is not opening up for us. It is closing around us slowly, galaxy by galaxy, on timescales of billions of years that feel geological from a human perspective, but are happening continuously and irreversibly. In the eternal limit, in the de Sitter space of the far future, The cosmological event horizon defines a finite region of space-time that is accessible to any given observer. This region is not infinite. It has a finite volume, and that finite volume has a finite number of distinct quantum states it can occupy. This is the de Sitter entropy. By analogy with the Bekenstein-Hawking entropy of a black hole, the region of de Sitter space accessible to an observer has an entropy proportional to the area of the cosmological horizon. This entropy corresponds to a finite number of quantum states, which means that the accessible region of the universe is, in a precise quantum mechanical sense, a finite dimensional system. A finite dimensional quantum system with a finite number of states is exactly the kind of system to which the Poincaré recurrence theorem applies in its strongest form. Not the approximate recurrence of a large classical system, but the exact recurrence of a finite quantum system, which, under the unitary evolution of quantum mechanics, must eventually return to every state near its initial state. The de Sitter horizon region will therefore recur, not approximately but exactly, on a time scale determined by the exponential of its entropy. For our universe's de Sitter horizon, this recurrence time is approximately 10 to the power of 10 to the power of 122 years. This number, 10 to the power of 10 to the power of 122, is the de Sitter recurrence time, and it deserves a moment of specific attention because it is the time scale on which the geometry of our universe essentially resets. Not the Poincaré recurrence of the observable universe, which requires the spontaneous fluctuation of an enormous number of degrees of freedom, but the exact quantum recurrence of the finite system, defined by the de Sitter horizon, the system within our causal reach. At the de Sitter recurrence time, our horizon region spontaneously returns to a state indistinguishable from its current state, with the same quantum fields, the same vacuum configuration, the same quantum correlations. An observer in that recurred state experiences a universe that, quantum mechanically, is identical to ours. They see the same night sky, feel the same physical laws, have the same apparent past. They are, quantum mechanically, us, in a universe that has recurred after an interval of 10 to the power of 10 to the power of 122 years. This is the ultimate horror of the de Sitter prison. Not just that the region of space-time accessible to us is finite, not just that we are locked behind a horizon that expands our cell while sealing off everything beyond, but that the finite system within the horizon is subject to exact quantum recurrence. And that recurrence produces, periodically and inevitably, states indistinguishable from the present, each separated from the last by an interval that makes every previous timescale in this video look like a negligible pre-dawn moment. Chapter 11. The thermodynamic arrow of time and what happens when it breaks. The arrow of time, the asymmetry between past and future that we experience as the unidirectional flow of time from past to present to future, is a consequence of entropy. The past has lower entropy than the future. Eggs break but don't unbreak. Memories point to the past and not to the future. Causes precede effects. All of this is a consequence of the fact that the universe started in an extraordinarily low entropy state, the Big Bang, highly ordered, highly specific, and has been increasing in entropy ever since. it is worth pausing on how fundamental this is to everything we experience. The fact that you can remember yesterday, but not tomorrow, is a consequence of entropy. The fact that you can affect the future, but not the past, is a consequence of entropy. The fact that a shattered glass does not spontaneously reassemble is a consequence of entropy. The fact that you age, that your body accumulates damage over time, rather than spontaneously repairing and growing younger, is a consequence of entropy. Remove the thermodynamic arrow of time, and you remove not just an abstract physical principle, but the experiential structure of every moment of every life that has ever been lived. The arrow of time is not a feature of physics that physicists study from the outside. It is the fabric within which all experience is embedded. Without it, experience as we know it cannot exist. The fundamental laws of physics, quantum mechanics, general relativity, the Standard Model, are essentially time-symmetric. The equations of fundamental physics work equally well in both directions of time. A video of elementary particle interactions played backward is, in almost all cases, indistinguishable from a video played forward. The arrow of time is not a feature of the fundamental laws. It is a feature of the universe's particular history, its low entropy initial state. In the dark era, past the death of all structure, in the eternal quantum vacuum, something peculiar happens to the thermodynamic arrow of time. The universe is in, or asymptotically approaching, its maximum entropy state. In the maximum entropy state, there is no thermodynamic distinction between the past direction and the future direction. The entropy cannot increase further because it is already at its maximum. It cannot decrease because that would violate the second law. The universe is in a state of thermal equilibrium, fluctuating around its maximum entropy configuration. In this state, the thermodynamic arrow of time ceases to be meaningful at the global level. There is no preferred direction. Fluctuations can occur in both temporal directions equally. A spontaneous fluctuation that briefly lowers entropy, producing a Boltzmann brain, or a small ordered structure, has no thermodynamic preference for occurring in the future rather than in the past. The distinction between past and future, which seemed so absolute and so obvious in the stelliferous era when entropy was reliably increasing, dissolves in the maximum entropy dark era. This has a specific and disturbing implication. In the dark era, an observer produced by a quantum fluctuation, a Boltzmann brain, has no thermodynamic basis for determining which direction of time is the past and which is the future. The low entropy configurations in its apparent memory, its apparent past, are not necessarily in the direction of lower global entropy, because there is no direction of lower global entropy. The arrow of time that the observer experiences is purely internal, a consequence of the specific configuration of its own fluctuation, and has no reliable correspondence to the external arrow of time that we use to navigate the world. In other words, a Boltzmann brain observer in the dark era cannot reliably determine the direction of time from thermodynamic reasoning alone. Its apparent memories are as likely to be false records of a future that has not yet occurred as they are to be false records of a past that never occurred. The arrow of time is an internal, local feature of the fluctuation, not an external, global feature of the universe. The Boltzmann brain is temporally unmoored. It exists in a moment it cannot place on a timeline, in a universe that has no preferred temporal direction, with memories that could be pointing in either direction of what it experiences as time. But there is a further consequence that is even more disturbing. Causation itself breaks down in the maximum entropy universe. Causation, as we understand it, the idea that earlier events produce later events, that the past is fixed and the future is open, depends on the thermodynamic arrow of time. In a universe without a preferred temporal direction, the concept of cause and effect loses its asymmetric character. Events occur, but no event can be said to cause another in any direction-independent sense. The universe in the Dark Era is not a universe of causes and effects. It is a universe of correlations, events that occur together in patterns determined by quantum probability, but with no privileged causal structure. The concept of one thing causing another, which underlies every aspect of scientific explanation and every aspect of agency and decision-making, ceases to apply in the maximum entropy void. This is one of the ways in which the eternal universe, in the Dark Era, becomes alien to every category of experience we have developed. We live in a universe with a clear thermodynamic arrow of time. Every aspect of our experience, memory, causation, agency, the sense of a fixed past and an open future, depends on this arrow. The Dark Era is a universe in which this arrow has dissolved, in which time runs symmetrically at the global level, and in which the local arrows of individual fluctuations are disconnected from anything external. The experience of an observer in the Dark Era, if it can be said to experience anything coherent at all, would be the experience of time without direction, present without past or future, existence without context, the awareness of a moment untethered from any sequence. Chapter 12. The Multiverse and Eternal Inflation. An infinite factory of horror. The horrors we have been discussing so far apply to our observable universe considered in isolation. A single universe that persists eternally and produces the events described through quantum fluctuation and thermodynamic processes. But there is a further layer of horror available if we take seriously the most widely accepted picture of cosmic inflation. The theory that the universe underwent a period of exponential expansion in its earliest moments, and follow it to its logical conclusion. Most inflationary models predict eternal inflation. In eternal inflation, the process of inflationary expansion does not end uniformly everywhere. Instead, it ends in some regions, producing bubble universes like ours, with a hot Big Bang and the subsequent evolution of stars and galaxies and life, while continuing in others. The regions where inflation continues drive exponentially rapid expansion, while the regions where it ends, the bubble universes, expand more slowly within the inflating background. The net result is that the total volume of inflating space grows faster than the rate of bubble universe production. Inflation can never be used up, because the inflating background always expands faster than the bubbles form within it. In eternal inflation, our observable universe is one bubble in an eternally inflating background, surrounded by other bubble universes, each with its own physics, its own constants, its own possibilities. The number of bubble universes produced by eternal inflation is not finite. It is infinite. The eternal inflation mechanism produces infinitely many universes, each potentially with different values of the fundamental constants, different particle contents, different laws of physics. This is called the inflationary multiverse, and its implications for the horrors of the eternal universe are both expansive and specifically terrible. In the multiverse, the number of observers is not just the number of observers produced in our single universe over its entire history. It includes all observers in all bubble universes, an infinite number of observers across an infinite number of universes with an infinite span of time. And within this infinite collection, the statistical arguments that produce the Boltzmann Brain problem become even more acute because the ratio of Boltzmann Brains to genuine observers must be calculated across the entire multiverse, not just within our single bubble. There is a specific problem in the multiverse context called the measure problem. In a universe of infinite extent or infinite duration, probabilities are not automatically well defined. Probability requires comparing the frequency of one type of event to the total number of events. But in an infinite universe or multiverse, both the numerator and the denominator of this ratio are infinite, and the ratio depends on how you choose to count. Different counting procedures, different measures, give different answers for the probability of any given type of observation. The measure problem is one of the deepest unsolved problems in cosmological theory, and it is unsolved in part because the answer depends on assumptions about the structure of the multiverse that we cannot currently test. The measure problem has a direct bearing on the significance of experience. In a well-defined probability theory, we can say that some outcomes are more likely than others, and this gives us a basis for preferring some explanations over others. In the inflationary multiverse without a well-defined measure, this basis is absent. We cannot say that our specific universe is more likely or less likely than any other. We cannot say that the specific history of your life is more or less probable than any alternative history, because the counting of probabilities across infinite alternatives requires a measure we do not have. Science depends on the ability to assess probabilities, to say that some hypotheses are more likely than others given the evidence. In the multiverse without a measure, this ability breaks down at the cosmological level. The multiverse is not merely a physical claim about what exists. It is a challenge to the foundations of rational inference. But the most disturbing aspect of eternal inflation for our purposes is what it implies about the existence of other versions of you. In an eternally inflating multiverse, every possible physical configuration that is consistent with the laws of physics in some bubble universe is realized somewhere. Not approximately realized, exactly realized, an infinite number of times. Every human being who has ever lived has infinitely many exact copies. In other bubble universes with the same laws of physics as ours, living lives that are, at the quantum level of description, identical up to some moment, and then diverging. Every decision you have ever made has been made differently by an exact copy of you in another bubble universe. Every outcome that could have happened in infinitely many exact copies, in infinitely many universes, all equally real, all equally physical, all equally incapable of communicating with each other across the inflating background that separates their bubble universes. The horror here is not existential in the sense of threatening your personal existence. You in this universe continue to exist for as long as your physical substrate supports you. The The horror is what the multiverse implies about uniqueness, individuality, and the significance of specific events. In a multiverse where every possible outcome is realized infinitely many times, the specific outcome that actually occurs in your universe, the specific history that you have lived, is not special. It is one of infinitely many equally real histories, selected by no mechanism more meaningful than quantum chance. The specific events of your life, the choices, the relationships, the losses and gains, are not uniquely yours in any cosmic sense. They are happening simultaneously in infinitely many variations, in infinitely many bubble universes, with infinitely many versions of you experiencing all the variations. The weight of any specific history dissolves in the infinity of alternative histories occurring in parallel. Consider what this means for any event that has felt significant. The birth of a child, the death of a loved one, a discovery that changed the way you understand the world, a choice that seemed to define who you are. In the inflationary multiverse, each of these events has an infinite number of variations happening simultaneously in parallel universes. In some, the child was not born. In some, the loved one did not die at that moment. In some, the discovery was made differently or not at all. In some, the defining choice went the other way. And every one of these variations is equally real, equally physical, equally happening right now in a universe separated from yours by a region of inflating space you can never cross. The specific configuration of events that constitutes your life is not the only version of your life that is happening. It is one of infinitely many, each equally physical, each equally real. This is not a comfortable picture. It is the picture that follows from taking the physics of inflation seriously and following it to its logical conclusion. The horror of the multiverse is not that it destroys you, it is that it trivializes you by embedding you in an infinity of alternatives that undermines any sense in which your specific experience is uniquely significant. Chapter 13. What lies beyond the end? The topology of forever. We have now walked through the major horrors of the eternal universe: the Boltzmann Brain problem, the Poincaré recurrence, the false vacuum decay, the death of the last black holes, the thermodynamic dissolution of the arrow of time, the de Sitter prison and its exact quantum recurrence, the inflationary multiverse and its implications for uniqueness. Each of these is grounded in established or plausible physics. Each represents a genuine implication of taking the universe's apparent eternity seriously and following the physics to its consequences. What lies beyond all of these, beyond the recurrences, beyond the Boltzmann Brains, beyond the de Sitter recurrence time, is a question that may not have a physical answer in the sense we have been working with. Because beyond a certain point in the eternal universe, the physical descriptions themselves break down, not in the sense of becoming inaccurate, but in the sense of becoming insufficient to say anything meaningful about what the universe is doing. Consider what happens after the de Sitter recurrence. The finite quantum system of our horizon region recurs exactly at 10 to the power of 10 to the power of 122 years. After the recurrence, it begins evolving again. It passes through the stelliferous era, the degenerate era, the black hole era, the dark era. It recurs again. It does this infinitely many times. Between each recurrence, there are Boltzmann brain fluctuations. There are smaller Poincaré recurrences of subsystems within the horizon. There are moments of spontaneous structure. There are moments of exact chaos. The eternal universe is not monotonous. It is infinitely varied within its infinite repetitions, and the variations are not small. But at some point, not a specific point in time, but a conceptual threshold, the question, what is the universe doing, ceases to have a stable answer. Not because the physics stops working, but because the universe is in a state of maximum entropy, with quantum fluctuations that sample all states equally over infinite time. Every state is realized. Every history is equally represented in the infinite temporal record. The universe is not being any particular thing, because it is, over infinite time, being everything. The question, what is the universe doing now, has a specific answer at any given moment, but integrated over the infinite future, the answer is everything, with equal frequency. What does it mean for the universe to visit every state with equal frequency? It means that the state containing the peak of human civilization is visited with the same frequency as the state containing a completely empty vacuum. It means the state containing your happiest moment is visited with the same frequency as the state containing a universe of pure radiation and nothing else. It means the state containing the full works of every civilization in the history of the cosmos is visited with the same frequency as a state containing a single photon. Over infinite time, in the maximum entropy dark era, these states are equally probable and equally frequent. No state is preferred. No configuration is special. The rich structure of the stelliferous era, the galaxies, the stars, the planets, the biospheres, the civilizations, the brief, warm miracle of life, is not the universe's default condition. It is a temporary excursion from maximum entropy, a fluctuation in the cosmic sense, no more representative of the universe's fundamental character than any other state it visits. This is the topology of forever, not a trajectory toward some final state, but a traversal of all states in a sequence determined by quantum probability. The universe, in eternal de Sitter space, is a random walk through the space of all its possible configurations, with no preferred direction, no final destination, and no external reference frame from which to observe the walk as a whole. It is, in the most precise physical sense, a universe of pure possibility without narrative, a system that realizes everything because it runs forever, but that achieves nothing in the sense of building toward any state that represents a completion or a purpose. The deepest horror of the eternal universe, I would argue, is not any specific event, not the Boltzmann brains arising from the quantum vacuum, not the Poincaré recurrences producing endless copies of every moment that has ever existed, not the false vacuum decay erasing the laws of physics, not the de Sitter horizon trapping us forever in a cell of finite quantum states. The deepest horror is the structure that underlies all of these events, a universe that never ends, that contains infinite time, and that produces events not because events matter or build toward anything, but simply because the laws of physics require that a fluctuating vacuum produce them. The universe is indifferent not in the sense of being cold or hostile, but in the precise sense of having no preference among the states it visits. It produces suffering and joy and consciousness and emptiness with equal impartiality, because it produces everything with equal impartiality over infinite time, without memory, without purpose, without end. This is what lies beyond the end. Not nothing, something much harder to sit with than nothing. An eternal machinery of possibility, producing everything and meaning nothing, running forever in the cold dark of the maximum entropy vacuum, occasionally flickering into configurations that include something that asks, in its brief moment of existence, what it is and where it came from. Conclusion. So here is what lies beyond the end of the universe, beyond the death of the last star, beyond the evaporation of the last black hole, beyond the dispersal of the last Hawking radiation into the expanding void. Time continues. The quantum vacuum persists. The laws of physics persist. And those laws, operating without interruption on the eternal vacuum, produce consequences that become more and more disturbing the more carefully you trace them. The Boltzmann brain nucleates from the quantum vacuum, a self-aware observer with false memories of a past that never happened, perceiving a world that does not exist, lasting for a moment before the fluctuation reverses. Produced with greater frequency than any genuine observer in the eternal limit, making the question, "Are you genuine?" unanswerable from the inside. The Poincaré recurrence returns every physical state that has ever existed, exactly, without gaps, an infinite number of times. Not as continuation, but as repetition, copies without connection to originals. The eternal return as a mathematical theorem rather than a philosophical challenge. The de Sitter horizon imprisons the observable universe within a finite quantum system that undergoes exact quantum recurrence at 10 to the power of 10 to the power of 122 years, beginning the cycle again with a state indistinguishable from the present, separated from the last recurrence by an interval that makes the universe's entire history to this point look like the opening fraction of a single second. The thermodynamic arrow of time dissolves in the maximum entropy dark era, leaving no preferred temporal direction, leaving observers untethered from any reliable sense of past and future, and taking with it the concept of causation itself, the bedrock of every scientific explanation and every human decision. The universe's memory of its own history becomes physically inaccessible, scrambled to the point of irretrievability, locked in correlations that no physical system within the horizon can ever extract. So that each fluctuation in the eternal vacuum occurs in a context without history, without memory, without any connection to what came before. The inflationary multiverse expands eternally around our bubble, producing infinitely many other bubble universes, with infinitely many other versions of every event that has ever occurred, trivializing the specific history of our universe by embedding it in an infinity of equally real alternatives and dismantling the very measure theory needed to say which outcomes are probable. And through all of this, through Boltzmann Brains and Poincaré, recurrences and de Sitter recurrence times, and the dissolution of time's arrow, the universe continues. Not because anything is propelling it forward, not because anything is waiting at the end, but because the laws of physics, which have no preference for ending and no mechanism for stopping, simply continue to operate. The universe is not running toward anything. It is not running away from anything. It is running because it runs, because time passes, because time passes. Because quantum mechanics requires that the vacuum fluctuate, and so the vacuum fluctuates, and so structures arise and dissolve, and so observers appear and vanish, and so everything that can happen happens, and then happens again, and again, and again, without end. This is the horror of the eternal universe, not the horror of destruction. The universe is not destroyed, not the horror of emptiness. The void is not truly empty, not the horror of finality. There is no finality. The horror of the eternal universe is the horror of continuation without meaning. A universe that goes on forever, producing everything, building to nothing, remembering nothing, headed nowhere, containing within its infinite duration every moment that has ever been significant and every moment that has ever been insignificant, with perfect impartiality for as long as time exists, which is forever. And somewhere in that forever, at an interval so vast that the number has no name, the quantum vacuum will fluctuate into a configuration that contains someone reading or watching something very much like this. They will sit with the same vertigo. They will feel the same unease at the physics they are being asked to accept. They will not know that the universe around them is, in all probability, not the genuine universe produced by a causal chain from the Big Bang, but a spontaneous fluctuation from the eternal vacuum of the dark era. A Boltzmann universe, complete in Zufälligkeit und every detail arising from nothing, lasting for a cosmic moment, and dissolving back into the void as the fluctuation returns to its mean. They will have all the same arguments for their genuineness that you have for yours. And those arguments will be exactly as convincing and exactly as inconclusive as yours are. They will not know. You do not know. That is the final horror. Not that the universe ends, that it does not, and that in the infinite time it does not end. It produces, among the infinity of things it produces, an infinite number of moments indistinguishable from this one, each inhabited by someone who thinks they are real, each of them uncertain whether they are, each of them unable to resolve the question from the inside, each of them dissolving back into the vacuum when the fluctuation that made them concludes. The horror is not in the darkness. The horror is in the light that occasionally flickers on in the darkness, asks a question, receives no answer, and goes out. And then, after an interval no language can express, flickers on again. The universe keeps going regardless. It has no choice. Neither in this sense do we, not in the sense of individual persistence, but in the sense of physical law, operating without exception, without preference, and without end. We are brief local departures from equilibrium in a universe that is returning to equilibrium and will remain there, fluctuating, for longer than any number that has ever been written. The departure is what we are. The return is what the universe is. And between the two lies everything we have ever called existence.